Okay, Chapter 2, Section 4, Equations of Kinematics for Constant Acceleration. So basically in this section, we're going to be introducing you guys to the kinematic equations that you're going to be using to solve for kinematic problems. So our first equation tells us that our final velocity equals to our initial velocity plus our acceleration times our time. Our next equation tells us our displacement is equal to 1/2 of our initial velocity plus our final velocity times our time. Our third equation tells us that our displacement is equal to our final velocity times our time minus 1/2 of our acceleration times our time squared. Our fourth equation tells us that our displacement is equal to our initial velocity times our time plus 1/2 of our acceleration times our time squared. And our last kinematic equation tells us that our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration times our displacement. Now, the most important thing about these kinematic equations is that they only work for constant acceleration. So they can only be used when your acceleration doesn't change throughout the problem. Thankfully, most of the time, our problems are going to tell us that our acceleration is constant, or we can assume that they're constant. So most of the time, we can use our kinematic equations. So a basic breakdown of the variables is that our x equals our displacement, our a equals to our constant acceleration, our vf is equal to our final velocity at time t, our vi equals to our initial velocity at time t, and our t is equal to our time stated or given. So most of the time they're going to give us our time, or we're going to have to solve for our time. Okay, so our check your understanding. This problem says the muzzle velocity of a gun is the velocity of the bullet when it leaves the barrel. The muzzle velocity of one rifle with a short barrel is greater than the muzzle velocity of another rifle that has a long barrel. In which rifle is the acceleration of the bullet larger? Okay, so thinking logically, we would say that rifle 1 has a larger acceleration than rifle 2, because it already tells us that rifle 1 has a greater muzzle velocity than rifle 2, and it has a shorter barrel, meaning that the bullet travels a shorter distance. And if something's going from rest to a high velocity in a short distance, it would have a high acceleration. So we would already say that rifle 1 has a higher acceleration than rifle 2. However, we can also use this using kinematics. So using kinematics, we would say that rifle 1 and rifle 2 have an initial velocity of 0 because the bullet starts at 0. And using the information given from the problem, we would say that rifle 1 has a final velocity of 8 meters per second, and rifle 2 has a final velocity of 6 meters per second. Now these are values that we just plugged in using information from the problem. It tells us that rifle 1 has a higher muzzle velocity than rifle 2, so we would give rifle 1 a higher value than rifle 2. And using the same thinking, we would say that the displacement for rifle 1 would be 3 and the displacement for rifle 2 would be 6. These are just values that we plugged in using the information from the problem again, because rifle 1 has a shorter barrel and rifle 2 has a longer barrel. So with the variables that we have and solving for acceleration, we would have to use the kinematic equation that our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration times our displacement. So if we were to solve rifle 1 in blue, we would say that our acceleration is equal to, I'm sorry, that's not right. Our acceleration is not equal to 58 meters per second. Our actual acceleration is 10.67 meters per second squared. And if we were to do the acceleration for rifle 2 in green, we would get that our acceleration is equal to 3 meters per second squared. So there we can see that using kinematics, we'd be able to see the actual values that we would get for our acceleration. And we see that rifle 1 has a higher acceleration than rifle 2. Okay, so problem 25 says a jogger accelerates from rest to 3 meters per second in 2 seconds. A car accelerates from 38 meters per second to 41 meters per second, also in 2 seconds. Find the acceleration of the jogger. Question B says determine the acceleration of the car, and question C asks does the car travel farther than the jogger during the 2 seconds? If so, how much farther? Okay, so we start off by writing our variables for the jogger, and we get that our initial velocity is 0 because it tells us that he starts from rest. Our final velocity is 3 meters per second, and our time is 2 seconds. Our variables for the car say that his initial velocity is 38 meters per second, and his final velocity is 41 meters per second, giving it a time of 2 seconds. So in order to solve our acceleration for the jogger, using the variables that we have, we would use the equation that our final velocity equals our initial velocity plus our time plus our acceleration times our time. So when we plug in our values, we get that our acceleration is equal to 1.5 meters per second. For part B, we would do the same thing. We would use the same equation because we have the same variables and we're trying to solve for the same variable. Therefore, once we plug in our values, we get the acceleration of the car is 1.5 meters per second squared. Now, they have the same acceleration, and in question C, in part C, they asked us, does the car travel farther during the does the car travel farther than the jogger during the 2 seconds? Since they have the same acceleration and it's during the same time, they would cover the same distance. So they would cover the same distance because they have the same acceleration and they are going over the same amount of time. Okay, question 24 says, in getting ready to slam dunk the ball, a basketball player starts from rest and sprints to a speed of 6 meters per second in 1.5 seconds. Assuming that the player accelerates uniformly, determine the distance. Okay, so accelerates uniformly basically means that it has a constant acceleration, so its acceleration doesn't change, which is good because now we can use our kinematic equations. So we start off by writing the initial velocity, which is 0 meters per second, because it tells us that he starts from rest. His final speed is 6 meters per second, and the time given is 1.5 seconds. So since we're trying to solve for x, and we have the variables of our initial velocity, our final velocity, and our time, we can use our equation that our displacement is equal to 1/2 of our initial velocity plus our final velocity times our time. And we get that our displacement is equal to 4.5 meters. So it's basically finding our variables and plugging them into an equation in order to solve for the variable they're asking for. And we get 1.5 meters equals to the distance that he runs. Okay, question 26 says that a VW Beetle goes from 0 to 60 miles an hour with an acceleration of 2.35 meters per second squared. Part A asks, how much time does it take the Beetle to reach this speed? Part B says a top fuel dragster can go from 0 to 60 in 0.6 seconds. Find the acceleration in meters per second of the dragster. Okay, so for part A, we would start off by finding the variables of the Beetle. We get that our initial velocity is 0 miles per hour, which is equal to 0 meters per second, because we have to convert to our SI units. And we would do the same thing for our final velocity, which is 60 miles an hour, which is equal to 26.82 meters per second. And they give us our acceleration, which is 2.35 meters per second squared. And we are trying to find the time. So the equation that we would use is our final velocity is equal to our initial velocity plus our acceleration times our time. So once we plug in those values, we get that our time is equal to 11.41 seconds. So that's our answer for part A. Part B, we will start off by writing the variables for the dragster. We get that his initial velocity is 0 meters per second. Final velocity is 26.82 meters per second because his final velocity is 60 miles an hour. And the time is 0.6 seconds. So here we can use the same equation as we did for part A because we have essentially the same variables except we're solving for our acceleration this time. So we get that 26.82 is equal to 0 plus our acceleration times 0.6, and we get that our acceleration is equal to 44.7 meters per second squared.